Okay, so what was your question?
So for number 22, it was the limit as x goes to negative 10.
Limit as x goes to negative 10.
Right. So like,
Mission 2, right?
so I put like negative 10 in. It was type 0 over 0. But then even when I thought like I did the right thing, but like 1 over x plus 10, even when I plug negative 10 in, it still doesn't work. So does that mean like it doesn't exist? Or like, am I doing the algebra wrong?
So no, I think you're doing the algebra right, and I think that one doesn't exist.
Oh, okay.
So, right, so there's a big difference between, if I
I
this,
didn't know if you couldn't, like, if that was possible.
no, so that one's from, that's the limit as x goes to minus 10 from the right. So if you look at problem 21 and 22, and you contrast them, you'll notice that they look very similar, right? But the one goes to 10, the other one goes to minus 10. There's a big difference between those, right? The one with 10, the x minus 10 cancels, but the one with minus 10, you got minus 20 over 0, right? So that's not the answer, right? That means that we need to think about it and explain how it diverges, right? Does it go to infinity? Does it go to minus infinity? Does it do neither? I mean, it's a one-sided limit, so it's probably going to be plus or minus infinity. 22.
Oh, 22, okay.
Yeah, sorry.
Thing was negative infinity to positive infinity?
It's either plus or minus infinity. You could try, let's see, minus 10, right? So we think about minus 10 to the right. So we should think about something a little bit, so to figure out whether it's plus or minus, what I'll do in a pinch is I go, okay, so I got minus 10. I'm approaching from the right, right? So I could try evaluating something like minus 9.9, for example. That would be here. And so that would give me some sense of what the value of the function is close to the limit point, right? So try plugging that into the, what was it, x minus 10 over x squared minus 100, is it? Yeah. Try setting x equal to minus 9.9. See what you get. Let's see. Did who had the? Was that mission 1? Okay, good. Now that I will post the solution to mission 1 here. Hopefully right after class. I already have it written and scanned. I haven't posted it because I was waiting for you. But generally speaking, in the future, I'll probably just post them and not wait for people because, but you had a special circumstance, so it's fine. But negative 99.7. See, I think that makes sense. If we, well, I got to think about minus 99.7. What is this equal to? This is equal to 1 over x plus 10, right? When you cancel it out. And what's the graph of? So it has a vertical asymptote at minus 10 if you want to graph it. And actually, I kind of think you should have gotten a positive number. Because if you plug in minus 9.9, it gives me minus 19.9. But then downstairs, I've got like 99 point whatever minus 100. So I got negative over negative. So I should get positive. And like graphically, that checks with my graph of the reduced function. Sure.
Any number you plug in, like as long as it's not 10,
Yeah, that usually works well. The closer the better. I think plugging in minus 9 is not, minus 9 might work, but you got to be aware that there are examples where interesting stuff happens at like minus 10 and minus 9, And for that kind of example, plugging in -9 ain't going to work. So the closer the better, as a rule. Well, yeah, I mean, but I think usually if you're not sure and you need to double check by plugging in some numbers, I would use like 0.1 away, 0.01 away. Yeah, and I don't usually put it into a calculator. I usually think about plugging it in and thinking hard about the sign that will occur in my mind. And then if I'm still a little bit like wishy-washy, I might make a graph of the function. You know, this is not a graph. Well, I guess the graph of this is what? It's this with a hole in it at 10, right? Like there's a hole here in the graph y equals the x minus 10 over x squared minus 10. So, and you know where that hole is. You figured it out in in like problem 21. You figured out where that hole is actually, because the limit as x goes to 10, you found what was it? It was 1 over 20, right? So that point right there, that hole in the graph is 10 comma 1 over 20. I know that from your work in 21. There's a big difference, of course, between 10 and minus 10, right? Minus 10 is vertical asymptote. 10 is just a hole in the graph. Both of these points, the reason, like, I think it's an interesting pair of problems because it illustrates that we need limits to analyze that kind of thing, right? But we can't just plug in the number minus 10 or 10. Yeah, the answer would be positive infinity. And you could either see that from like looking at a table of values or just looking at some values close to plugging in the limit point, or from a graph. Or you could also rely on the system of notation I've used a couple times in examples. Like, so I said, okay, so x approaches minus 10 from the right. Basically that says x is equal to minus 10 plus some little positive delta, right? So if I plug that into, so if I look at 1 over x plus 10, which is the simplified version of that limiting function, the function you're limiting, right? And I plug that in, I get 1 over minus 10 plus 10, minus 10 plus delta plus 10. So the 10s cancel, and you're just left with 1 over delta, right? So that's 1 over a very small positive quantity, which shows me that the limit is tending to infinity. So if you don't like plugging in minus 9.9 because it's an ugly decimal, you can do a little bit of algebra by putting in like the limit point plus or minus delta for a left or right limit. This is, actually, if you wanted to use this system of algebra on a double-sided limit, you could do something like analyze minus 10 plus or minus delta, where you carry plus and minus case at the same time with that plus minus notation. But I don't know. These are strategies. So I'm sorry, I just told you 3 different ways to solve this problem. Any one of those would work. Yeah. So you guys are not going to hold it against me for showing you more than one way to do a problem, because like last semester pre-calculus, my course evaluations, not so great. You should not explain things to pre-calculus. You should just do. You do them. You don't explain them. So. Other question? Yep.
So, on number 29,
Mm-hmm.
like it was 1 over t minus 1
What?
over t squared.
Plus t? Yeah.
To the 0. What did I even do?
So you got 1 over t squared. Is it minus 1 over t squared plus t?
Yeah.
And that was the limit as what? T goes to 0. Is it type 0? Well, I mean, that's 1 over 0. That's 1 over 0. But they don't have the same denominator yet. I mean, I would look at this as, well, is it t squared plus t? Huh. I mean, I would make a common denominator and go from there. At the moment, it's type infinity minus infinity, which is indeterminate, you know? That's an indeterminate form. So, I mean, what I would do would be make a common denominator. So there are various strategies for making a common denominator. One is to look for the least common multiple of the denominators. That involves thinking. A lazier way is just to cross multiply, you know? I think I would just cross multiply here. In other words, if I've got something like a over b minus c over d, the algebra step I make is a d minus bc over bd, which amounts to multiplying the first one by d over d and the second one by b over b, so that they have a common pattern of b over b. I mean bb. So like I multiply this one by d over d, I multiply this one by b over b to get what's over there. So they have a common denominator. Now here, I'm saying like the pattern here would be b equals t squared, and my denominator in the second fraction is t squared plus t, right? So at the risk of solving your problem, I'll write one more step. Limit as t goes to 0. So I get t squared plus t on this one, right? Minus 1 times t squared, which is just t squared, divided by t squared times t squared plus t. So many t's.
So the one t squared plus t at the bottom of the canvas.
Well, the t squared's upstairs. They cancel out, right? And this t, basically you can think of as canceling with that t squared. It just leaves you what? Looks like, I think we get 1 over t times t squared plus t, right? If I haven't made an algebra mistake here.
So you would multiply the t in, or?
Sorry, what's that?
You didn't have to multiply that t in?
Oh, you could if you want. Sure, go for it. What did that give you?
Oh, okay, but like, is that an answer? Do we have to?
Well, I guess that's my question: is what's the answer? Can I erase this algebra jibber jabber? So, what happens as we plug in the limit point now? You're very hypocritical. You say the limit, you don't plug in the limit point. Yeah, you're always plugging in the limit point. Why make up your mind, right? But you notice like there's a logic here, right? If I plug it in and it doesn't make sense, then I have to kind of back up a second and go, what happens to the left? What happens to the right? Do they match up? If they match up, then great. If it's infinity or it's minus infinity. If they don't match up, the limit doesn't exist, right? But here, plug in 0, we got 1 upstairs, we got, 0 downstairs. And I can see that it's 0 downstairs whether or not I multiply that out, so it doesn't really matter whether or not you multiply that out. Because 0 times 0 is just 0, you know? I don't think I gain anything by multiplying it out, is what I'm saying. There are other problems where multiplying it out would be worthwhile. Right. You could graph, you could try plugging in a number. Now, I guess, yeah, you know what? Here, I think we can actually graph. I was kind of scared to graph by hand, but now that you mention it, this is 1 over what? T squared times t plus 1, right? So that, what does that have, graphically, what does that look like? There's 2 places it has vertical asymptotes, right? T t equal to 0, t equals minus 1, right? And I can see from that t squared there that it's going to go to, well, it's going to go to infinity on both sides. Because the t squared is going to give you like a volcano that 1 over t squared is going to graph to like a volcano. I mean, we could plug in a number. Try plug in 0.1. What happens? 0.1, I get 0.01, I get 1.1, right? Positive. Try plugging in minus 0.1. I get 0.01 because the minus gets killed, and I get 0.9. So I get, you get positive both sides of the limit, so this one is infinity. I'm sorry, I seem to have solved your homework problem. You will forgive me?
Yeah.
Okay. But yeah, once you get something like, when you face something that when you plug in the limit point, it doesn't make sense, that means we have to do algebra to like remove the indeterminacy one way or the other. All right, so I'm going to go on to the new material at this point. I want to talk to you guys about the definition of continuous function. So I'm going to start with a somewhat formal definition, all right? But we will soon leave this. I'm stating this for this sake of generality here, but we'll soon replace this definition with statements about limits, okay? So here's the definition. Let f be a function. All right. And A is an element of the domain of f. That's important. So we can only talk about the continuity of a function at a point in its domain. All right? Ooh, why have I used that? It's foolish, very foolish. All right, so here we go. Then f is continuous at A if and only if for each epsilon greater than 0, there exists delta greater than 0 for which 0 less than, actually this time, no 0. This time, no 0. For which the absolute value of x minus a less than delta implies the absolute value of f of x minus f of a is less than epsilon. If f is continuous for each a in U, then f is continuous on U, and then we say f is continuous if it is continuous on the domain of f. So I've defined 3 things here. This is my definition 3.6.1, which is on page 130 of your notes. All right. So, so first of all, I define continuity at a point, right? So what it means for it to be continuous at a point. Then I've defined continuous on a set, all right? So it's continuous on a set if it's continuous at each point in the set. And then finally, continuity of the function itself means it's continuous at each point in the domain. So that's the definition. Now, what does this remind you of? It should remind you immediately of our definition of limit, right? Like our limit definition was much the same. We had for every epsilon greater than 0. What was the difference about the limit, though? The limit definition we had a 0 beneath here, right? And we didn't have f of a here, we had L, right? For the limit as x approaches a of f of x equals to L. So it's kind of the same. I would just say this. It's like the limit as x approaches a of f of x equals to L, but here L is equal to f of a, and we do not forbid x equals to a in the analysis, right? So in your notes, I have a couple different pictures to try to help us understand continuity, like some sort of graphical perspective. Essentially what it means if the function is continuous is that the graph has points which are kind of stuck together. So I'll draw some pictures over here. So there's different cases, right? The first and kind of most boring case would be when a is sort of in the middle of the domain of the function, right? So maybe the function's graph looks like this. I don't know. So I put y equals to f of a here, and the vertical line is x equals to a, right? And the blue is just y equals f of x. So what does continuity mean? Continuity to a means that you pick any epsilon you like, right? What does this condition, absolute value of f of x minus f of a less than epsilon mean? Absolute value of f of x minus f of a less than epsilon. This means f of x is within epsilon units of f of a. It says that's the case, right? So the logic of the definition is we pick any epsilon greater than 0. So I usually graph it as a small epsilon because that's what it's most interesting for. Oops. I need to make a more exciting graph. Here, I'll make a more exciting graph here. Whee! There we go. So we pick an epsilon. I mean, you're faced with an epsilon band like that, right? And then you have to be able, if it's continuous, that means that the points on the graph are stuck together, right? Which means that if you make the zoom window small enough, none of the function should jump outside the zoom window. And we set the horizontal, so we have to say, okay, for a given vertical zoom like that, we can squeeze the horizontal enough so that the graph is stuck inside there. So for this one, as pictured, I could make the delta something like this. Right? Now, if you can't choose a delta, so here's x plus delta, or a plus delta rather, or a minus delta. If you can't choose a delta to pinch the graph inside the zoom window, then it's not continuous. But one of the big differences between this and the limit is that we actually consider the point in the middle, right? You can't have, like we were just talking about for your homework, where we're taking limit as x goes to minus 10. We look at values close to minus 10, but not minus 10 itself. Like it's different. We have to consider the limit point here for continuity. So now, if you'll forgive me, to not waste an inordinate amount of class time, let's just focus on this one picture here. What would happen if the domain of the function had an endpoint at a? How would this picture change? See, if the domain has, if like the function is only defined to the right, you'd have a picture that looks like that, right? then if you look at this condition here, what does the definition reduce to? It reduces to the limit as x goes to a from the right of f of x equals to f of a, right? If a is a left endpoint or left boundary point, right? On the other hand, if the picture is like, so, you know, the function is defined over here, and then it ends there, but that's the end of it, you know, then continuity at a would say that the limit as x approaches a from the left of f of x equals to f of a, right? A is a right boundary point. And then the picture I had to start with was what? A was not a boundary point, right? A was in the interior, what we would say is the interior of the domain of f, right? So if it's in the interior, then we go back to our original picture like this, and we could just write the double-sided limit, right? A is in the interior of the domain of f. So this one definition covers all three of those cases. That's why we like the epsilon delta definition, is it simultaneously covers endpoints and middle points. And not that it matters to our course, but it also makes a sequence by default continuous. Like a sequence is a domain from the reals. A sequence is a function whose domain is the natural numbers. So like a sequence, every point in the domain of a sequence is isolated. So you can't really calculate a limit for those points. But even with that, with a sequence, if you go through this definition, you can see a sequence is actually by default continuous according to this definition, which has a certain theoretical appeal. And that's all I'm going to say about that here. So we have a theorem. What's our theorem? So the theorem is simply this. F is continuous at a in the domain of f, if and only if what? The limit as x approaches a of f of x is equal to f of a, or the limit as x approaches a from the right of f of x is equal to f of a, or the limit as x approaches a from the left of f of x is equal to f of a. I could find probably a better way to write this, but what I'm saying is it's continuous at a point in the interior if and only if the double-sided limit matches, right? By the way, we have a theorem that says if the double-sided limit exists, the left and the right limits exist and have to match up, right? I've given you a few homework problems that actually are based on doing that. Actually, I wrote those homework problems. I haven't shared them with you. I've written home missions 3, 4, and 5 already. I need to post them. But, you know, you wouldn't know about that, right? Unless you were, like, stalking me. That's unlikely. Now, this, on the other hand, is what we want to... This is a condition for continuity at endpoints, all right? So, in short, a function is continuous if and only if the limit of the function is equal to the evaluation of the function in the appropriate way. That's our sort of intuitive backdrop here. Okay, so that's what we mean by continuous function. So guys, I think I am my own worst cameraman, you know. All right, so let's oh man, I got to get some juice. So let's talk about, oh, by the way, if you want to see what discontinuity looks like, I have a picture on page 131. You should look at that one, right? I here, see this one here. So take a look at that one later when you're looking at the notes. That'll show you what discontinuity looks like. Basically, there's, if there's a jump in the graph, we can't satisfy the epsilon deltas. This is the same picture we talked about for showing the limit doesn't exist. So like that one illustrates like discontinuity is when the function is not continuous at a point. So, so I guess my next question for you would be, depending on how good your memory is from pre-calculus, we may or may not have a disagreement about what I mean by a continuous function. All right? So what is a continuous function? So I just told you, essentially, the limit as x goes to a of f of x is equal to f of a, for each a in the interior. Do you guys know what interior is? What's that? It's the inside, right? So the interior of a set is away from the, it's everything except for the boundary points, actually. So if you can put like a little open ball around the point, then it's said to be an interior point. It's exactly what it sounds like. It's the inside of the set. Now, if the only kind of points you have are isolated points, then there's no interior to the set. That's just kind of a quirk. Anyway, so let me stop talking about isolated points. That's really almost completely removed from our experience. But what was your definition of, did anybody remember what was your definition of continuous function in pre-calculus? What was a continuous function? Did you guys talk about it? No? Don't remember? Sometimes the definition for continuous function is given, a continuous function is one for which you can draw the graph without lifting your pen. Sometimes that's given as a definition. Can draw y equals f of x without lifting pen. That's often the pre-calculus definition of continuous. We actually don't agree with that here for the following reason. Let me show you an example. So f of x equals to 1 over x. What's the domain of this function? I'll write it in interval notation. Minus infinity to 0, union with 0 to infinity, right? Or if you like, you could say the real numbers with 0 removed, right? This is the domain of 1 over x. Is the limit of this, so this function, does the domain have any boundary points? The domain has one boundary point, actually. Well, is that a boundary point? I don't know. I forgot my definition of boundary point. But the only kind of funny point here is 0, right? 0 is the point not in the domain. But because it's not a point in the domain, we can't ask the question, is the function continuous at 0? Our definition of continuity requires us to look at points within the domain of the function. So the question, is 1 over x continuous at 0, is not even defined in our lexicon of ideas. So there's the distinction between calculus and pre-calculus. Pre-calculus will talk about what the function does at a point outside its domain. And that's a useful device for graphing. But here, I mean, look at it. The limit as x goes to a of 1 over x, well, we can work it out. That's equal to 1 over a for a not equal to 0. That limit law proves that the reciprocal function is continuous at every point in its domain, which means that this function is a continuous function. And yet, can you draw its graph without lifting your pen? I can't. Right? Because the graph of the reciprocal function is this. Right? It's got this vertical asymptote at the y-axis, right? So this slogan, a continuous function is one you can draw without lifting your pen, it assumes something. For us to make that statement true, we have to tack on a condition. We have to say a continuous function with connected domain is one that you can draw without lifting your pen. A continuous function with connected. What's connected mean? I'll say it's drawn in one stroke. I'm tired of writing lifting a pen. A connected domain, what are the connected subsets of the real numbers? These are called intervals. And also just a set containing just one point is kind of a stupid example of a connected domain, but the connected domains of the real number, these are like opened intervals, closed intervals, half open, half closed, raised to infinity, raised to minus infinity. Oh, this is function. It's my abbreviation for function. Yeah, it's all good. So, I mean, actually, this is kind of funny. What is a connected domain? A connected domain is one which you can draw on the number line without lifting your pen. So, yeah. All right, well, let's get to it. I mean, so the natural question then is, so, all right, so if 1 over x is continuous, right? I'm not saying it's continuous at 0. I'm just not saying anything about 0. Well, I can say something about 0. We can say 0 is a vertical asymptote because we have limits of plus or minus infinity at 0, right? Okay. So here's a theorem. If f and g are continuous at x equals to a, then number 1, f plus g, number 2, c times f, number 3, f times g, number 4, f over g, provided g of a is not equal to 0, right? All 4 of these are, guess what? Continuous at a. So we can build new continuous functions from old by adding them, multiplying by a number, multiplying the functions, right? And even dividing the functions. What's the proof? How would you prove that? So, for the sake of brevity, we're going to assume A is an element of the interior of F intersected with the interior of G. I don't know if you thought about this or not, but when we add or multiply functions, the domain of the addition of two functions or the multiplication of two functions is the intersection of their domains by default. Because we have to have a point for which both of the formulas for F and G make sense. That's intersection. So I'm saying A is a point in the interior, so we can just look at the double-sided limit, right? And so the proof of 1, it's very silly. Check it out. Limit as x goes to A of F plus G of x. What's that by definition? How do you define the addition of two functions? That's point-wise defined F of x plus G of x, right? But then by adding the additional offer limits, we can write that as the limit as x goes to A of F of x plus the limit as x goes to A of G of x. But F is continuous, and G is continuous by assumption, so what's the limit as x goes to A of F of x equal to? I mean, I said this was a theorem today. A lot of other people in Calculus 1 would say the definition of continuity for a function is that the limit as x goes to A of F of x is equal to F of A. And they wouldn't be wrong. They're just limiting the discussion to interior points. So this, by definition of continuity, is F of A. And this, by definition of continuity of G, is G of A. And by definition of addition of functions, that's F plus G of A. So that shows that the function F plus G, as x goes to A, has value that's given by evaluation. That shows that F plus G is continuous at A. So would you guys know how to prove 2? How about, I'll leave 2 to you. How about number 3, what would do? Limit as x goes to A of fg of x. That's the limit as x goes to A of f of x g of x. By definition of the product of two functions. But then by the product rule for limits, which is actually a kind of a pain to prove. I didn't really prove it in class here. I gave you notes that have like a page-long proof of it. It's kind of a pain. But by the product rule for limits, this is x goes to A of f of x times the limit as x goes to A of g of x. I can make that step because I know that, see, whenever you do something like this, we're taking out a logical loan, because that step's only allowed if you know that the limits I just wrote exist. How do I know that those limits exist? Well, I know they exist because I'm assuming that the functions are continuous, which means that the limits exist and are given by f of A and g of A, right? Without that knowledge, that step I just made doesn't make sense. Like you could, in your homework problem, you had limit, that 1 over t minus 1 over t squared plus t problem. You could not reasonably write the limit of what's originally there is equal to the limit of the first term minus the limit of the second term. Like you could not do that because those two terms separately don't exist. They have non-existent limits. You can't apply limit laws to non-existent limits. Something to keep in mind. But this is f of A, g of A, and so we're, back to the product of f and g evaluated A, so therefore that proves that f times g is continuous at A. All right. So the proofs are not especially exciting, but there they are. And the quotient rule, I can't talk. The quotient rule for limits gives you the other one. Now, I've separated off the composite rule for limits on its lonesome here because composition always gives us a little bit more trouble. So I thought it was worth having its own sort of standalone theorem. So here it is. Theorem. If f is continuous at A. And G is continuous at f of A, then G composed with f is continuous at A. So the proof of this relies on the composition of limits rule, which basically is a rule that says you can substitute the inside function as a variable for the limit when you're faced with this kind of problem. So let me write it out actually. So the proof is essentially this. We're looking at the limit as x goes to A of G composed with f of x. What's the rule for the composition of functions? How's that work? So the formula for G composed with f of x is G of f of x. Right? This is the composite composition of G with f. F is the inside function, G is the outside function. And the rule was, by our composition of limits rule, we can replace this with the limit as y goes to the limit as x goes to A of f of x of G of y. That was the composition of limits rule that we had before. But what do we know here? We know f is continuous, right? So what is limit as x goes to A of f of x equal to? So this right here is proposition 3.3.10. So f is continuous. What is this limit equal to? FA, right. So we have the limit as y goes to f of A, of G of y. Can you simplify this for me? G is continuous at f of A. What's the limit as y goes to f of A of G of y equal to? Right. That's G of f of A. But that's nothing more than the composition of G with f evaluated at A, which again goes to show you that the composite of continuous functions is itself continuous. So sum, scalar multiple, product, quotient, composite of continuous functions are all continuous at appropriate points. You start to wonder what on earth is not continuous, right? It's actually fairly hard for me to come up with an example of a non-continuous function using just formulas, the way we've defined continuity in here. All right. So in fact, the elementary functions, elementary functions, what do elementary functions include? Remember, polynomials, sine, cosine, exponential, logarithms, hyperbolic functions, the inverse functions of all these things, like cosecant, secant, tangent, cotangent, all these things. All of these functions are continuous on the interior of their domain. So let's see here. Now I can give you an example of a function which has, let's see here. I'm trying to think if this counts as a discontinuity for us. See, I think that, the point is every place where there's what you'd like to call a discontinuity, it happens outside the domain of the function. Unless you make like a special sub-definition for it. So let me show you what I mean. for example, if I have f of x, we talked about this last time, I think, x over the square root of x squared. Remember, this is x over absolute value of x. So what is that defined to be? It's defined to be 1, well, minus 1 if x is less than 0. It's 1 if x is greater than 0, right? So notice that we have limit as x goes to a for a less than 0. Limit of x goes to a of f of x equals to, minus 1, which is f of a, for a less than 0. And we have for a greater than 0, this works out to 1, which is also equal to f of a for a positive. That's everything in the domain. So this is a continuous function. Now this bothers some people to say that, right? Because you'd like to say that this is, in fact, I probably am guilty of saying this already, that this is a discontinuous function, right? But when I say that, I'm not saying that from the perspective of carefully defined continuity of functions as the sense we've defined it today. That's from a pre-calculus terminology. Now, I could make this function discontinuous. Check this out. If I let g of x equal to, forget about the formula, minus 1 for x less than or equal to 0, and 1 for x greater than 0. That's almost the same function, right? What's the difference? I just filled in that dot. And that's all it takes. That's all it takes to go from, in our language, continuous to discontinuous. Because now we would have the limit as x goes to 0 of g of x what? It does not exist, right? And if it does not exist, it can't be equal to g of 1. And once I fill in that dot, 1 is a point in its domain. So anyway, all I'm telling you is it almost forces me, if I'm going to give you a function which has a discontinuity, short of some creativity on my part, it seems like it can only happen in a case-wise defined function, where I've sort of ham-handedly stuck in the point at the gluing point. Because all right, anyway. Another good example would be tangent. What's tangent look like? See, tangent has vertical asymptotes all over the place, right? Every pi. It has one at pi over 2, it has one at minus pi over 2, and then the tangent is pi periodic, right? It repeats itself every pi. So but the thing about the tangent function is it is continuous on its domain. The thing is, the place where we'd like to say it's discontinuous, those are points outside the domain. So, I guess we could take the somewhat, see, people want to have their cake and eat it too, right? They want to have a definition of continuity which matches the careful definition of continuity which is used in higher mathematics, abstract mathematics, like what's called topology. Topology is the study of continuity in the abstract, right? And so the definition I've given you of continuity is in line with the topological or analytical way of thinking of it, higher math. But that runs counter to our common language in pre-calculus of discontinuity, right? So what do we do? I don't have a good solution to it. I think maybe one way we could just make this would be kind of a tacky solution. We could just say, well, you can talk about points of discontinuity outside the domain, but you can't say it's not continuous there. Let me shut up. Anyway, a wise person would avoid this discussion. Of course, I've made it a 20-minute talk. All right, so in short, each function, polynomial, rational, algebraic, trigonometric functions, the reciprocal functions, exponential functions, and even the hyperbolic trigonometric functions are continuous on their domain. Let me keep harping on the hyperbolic functions here real briefly. So, I would say please read theorem 3.6.7, which has all the claims I just had in there. One of the claims is that, let's see here, like 6 hyperbolic functions continuous on R. So let's look at that. The limit as x goes to a of hyperbolic cosine of x. What's that equal to? Be cosh a, right? But, you're right. Let's see why that's true. Limit as x goes to a of 1/2 e to the x plus e to the minus x. That's the definition of hyperbolic cosine. So then we can pull the half out, and we have the limit as x goes to a of e to the x plus 1/2 limit as x goes to a of e to the minus x. Now, e to the minus x I could also write as what? 1 over e to the x, right? Like, instead of writing this, let me write that as 1 over e to the x, just to emphasize something. So if I know the limit, if I know that the exponential is a continuous function, right? And I have a partial proof of that in the notes, but I haven't gone over it in class time because it's technical and not particularly interesting. But you can give arguments to show that the exponential function is continuous. All right, so that is e to the a, and that's 1 over e to the a by the quotient rule for limits, right? But then putting things back together, we have what? Just what you told me, cosh of a. All right, so, and what would the proof for sinh look like? Almost the same. It's just instead of having a plus, you have a minus for the hyperbolic sign. Hyperbolic sign is the same, but with a minus instead of a plus here. Okay, so let me just try to summarize everything. What I'm saying is that all of the functions that we know and love, the elementary functions, are continuous wherever their formulas make sense. So we can't say that a rational function is continuous at a vertical asymptote. Actually, we can't even say it. We can't even open the discussion because we don't define continuity outside a point in the domain, according to our definition. Right? But of course, pragmatically speaking, points outside the domain can be very, very influential in the shape of the graph, right? So vertical asymptotes matter. Holes in the graph can matter. Those are also points outside the domain. Okay, so that's pretty much it for continuous functions. So it's not that complicated, right? They're just a function that you can calculate the limit by evaluation. What's interesting about continuous functions, though, is what I'm about to tell you, which is called the intermediate value theorem. So intermediate value theorem, or IVT as we'll often abbreviate it past this point, theorem. It says the following: suppose f is continuous on interval a to b,